this. First point, can everybody sign the little sheet of paper that's coming around that's saying you're attending, so that we've got a complete record of who's here tonight. I appreciate that. Tonight, it gives me great pleasure to introduce Bob Stuart, Meridian Audio. It's Keith Howard, who you also know, and we're going to talk through some of the many, many engineering things Bob has done in his life. And I've known him since we were both in our 20s, and he's worn better than me, back in the Cambridge University Tape Recording Society days, because I can remember you turning up to those.
That's right.
And I can remember young Heather Lane turning up with Basil Lane occasionally as well, so that dates us all.
She was lovely then, wasn't she?
She was lovely. Is this where you go for brothers? And this is the only guy in audio engineering who sat in my front living room when, in the early 70s, mid-70s, if we're lucky, listening to different amounts of feedback on amplifier with a rather ropey Garrel turntable.
Early 70s, yeah.
Early 70s. Yeah. So I won't leave you to work out the difference between then and now, but there's a lot of water gone under the bridge. And Bob has gone on to do many great things, being a fellow of the Audio Engineering Society, a lot of work on active loudspeakers, and a great deal of work with colleagues on the advancement of high-resolution audio. And I hope we're going to hear some of those things tonight. And that's where I'm going to stop and hand the field over to you.
If I can just address a comment to the audience before I start talking to Bob, when we've had our photograph taken.
Mark.
Thank you, Mark. Bob and I thought that just to have talking heads sitting here, going through the various topics and things that he's made his name in, would be a little bit dull, trying to paint pictures with words. Much better for Bob to prepare some material to support various topics that we're going to talk about this evening. So we don't know quite how well this is going to dovetail together, but basically what's going to happen is I'm going to talk to Bob to introduce some topics by asking a question, and then he's going to do some presentations to you, and then we'll move on to another topic, and there'll be further presentations, and we'll busk it and make it work somehow, but it may not be the smoothest thing that you've ever seen. Well, we didn't have a chance for rehearsal, did we, Bob? So.
Well, that's because you didn't tell me what the questions.
Not quite. Yes, just to let you know, if this isn't too rehearsed, we have talked about the topics, but we haven't talked about specific questions, as you would hope. Firstly, Bob, thank you for agreeing to take part in this. I expect you realise it's the first time that we've done something like this. So if it works well, we'll do it again. If it doesn't, it'll be forgotten about in perpetuity. So, so no pressure then, Bob. Okay. I'd like, if I can, before we go on to talk about specific items of technology, I'd like to ask you if you could fill us in a little bit of background about your early years, because I've read interviews that you've done, obviously, and I've done a few with you in my time as well. Read your biographies in the JES and elsewhere, which tend to start with you studying electronic engineering at Birmingham University, as I understand it, where you also developed your interest in psychoacoustics, but nothing before that. So did you arrive at university deciding you were going to be an audio engineer, knowing you were going to be an audio engineer, or were you were? Okay, so what were your early influences?
From the age of 15, I knew I wanted to be an audio engineer.
Okay.
Right. Early influences. Well, I've always been passionate about music, and back then I used to sing. Don't do it so much now, but music's always been important. And
so you came from a musical family?
I suppose you could say that.
Yeah.
Yeah, I suppose you could say that. And so music was important. As a student, I needed to be able to play back my music, so one had to design the equipment. And in fact, before I went to university, I designed a tape recorder. Bought the tape deck and did all electronics, and actually published it while I was working. Right. So that was the beginning, and so I went to university. In fact, I sought out a university that could do acoustics, psychoacoustics, and electronics. And at that time, there was only 3. These days, it's much easier.
Sure.
Yeah.
But Birmingham got the vote. Then.
Yes.
Okay.
Right.
And was that because there was a specific person there who you wanted to be taught by?
No, I think I thought Bangor was too far to go. And it was a good department.
Yeah.
Yeah.
Okay. Now that those articles
As
that...
it turned out, there was a great person there, Professor Jack Allison, who was very good on psychoacoustics.
Yes.
Wrote several books, was a brilliant mentor.
And this is a theme we're going to return to because you're, if not unique, very close to being in the high-end audio industry and actually having a deep interest in psychoacoustics, actually applying it to the design process.
Yes. Well, he was absolutely brilliant because he understood the topic and he taught the topic. But he also taught lightning empiricism and, you know, things I've always enjoyed, which is trying to design things with very quick thought patterns.
Okay.
Yeah.
Now, that Wireless World article was not the one I'm about to mention, I think, because for most people of a certain age in the audience, you will probably have been a blip on the radar initially as a result of the series of 6 articles that you wrote for Wireless World, An Approach to Audio Amplifier Design, starting in August 1973.
Yes.
How did those come about?
Well, I'd been, when I was at university, I'd done the tape recorder thing, and I wanted to understand how to design a power amplifier, because that's a bit scary. And I spent a long time studying it, and discovered some things, and decided to write up an article for Wireless World. It was a series of 6?
6, yes.
Wow. Anyway, that got me into a lot of trouble, because I talked about the sound of amplifiers, and I got hauled up on the headmaster's mat. And I'm talking Peter Walker and Peter Baxendale. As a very young man.
That must have been quite daunting.
Being challenged. But yes, it was daunting. But I mean, Martin here, I remember all of that, because that was the time when amplifiers were not allowed to sound different.
Sure.
And there was a lot of debate about it. If it's flat from 20 to 20 and you can't hear the distortion, it's all right when the band's playing, sort of thing that Peter used to say to us.
Yeah. And then after that, for a brief period, you became a consultant, as I understand it, and you were involved in Lexon, for example.
While I was at college, I, quite by chance, got a consultancy opportunity to work for Cambridge Audio, and that got me into the audio business directly.
Okay.
So I fixed some things for them, and quite soon after leaving university was then invited by David Southard, who was the man who ran Cambridge Audio, but had then left to start up a company called Lexon, which you may remember.
Yes, indeed.
And that was the first time I really got involved in audio, and the first time of many that my mother said to me, "Aren't you going to get a proper job?"
I'm intrigued as to whether the Lexon experience was formative in the sense that when you went on to form Meridian, Boothroyd Stuart Meridian as it was in 77, you did something quite unusual at the time in that you established a company with an industrial designer.
Yes.
So it appears that at the time when people were actually quite happy sticking hi-fi in all sorts of ugly shapes and
I got a picture
boxes.
of it here if you want to put this projector on.
Yeah.
That's
Yeah.
it,
The Lexon.
it
Now,
was-
had you decided before this that was what was needed in hi-fi, the combination of...
No. I was interested in the technology of the
Right.
sound. So I was interested in, by that time, I was deeply involved in analysis of active speakers, amplifiers, and so on. So it was, able to design all these bits and pieces reasonably well. It was David Southard who put Lexon together, who had the prescience to think that industrial designer was needed. If you remember, Cambridge Audio was a very good-looking product.
Yes.
It was actually designed in the Bauhaus style. In
Mhm.
fact, it was designed by Bauhaus consultants. So the idea of having an industrial designer on board was quite new. But Al and I hit it off right then, and we're still at it. The Lexon was our first product, and Martin was the first person to review it.
Right.
On the front cover of a magazine edited by Heather's husband.
Hi-fi for pleasure.
Exactly.
Yes. So after that, it clearly was a formative experience then as far as the importance of the industrial design side.
Oh yes, lots and lots of mistakes. And inside this, and Lexon itself, I learned a lot about business, about, we had a bit of bad luck in Lexon. We had the 3-day week and the winter of discontent and
Yes.
so on. After that, Al and I started a consultancy called Boothroyd Stuart, curiously. And we got several jobs doing loudspeakers, but also we designed the Orpheus. Remember the Orpheus?
Yes.
This one. And this was designed for a company that wanted to get into audio. And it was really quite an advanced product at the time. and Alan was doing industrial design work of all sorts. For example, he did the Sinclair, the Black Watch, the first calculator, all sorts of different things. I just did audio. And this company, just at the point we finished the design, they went into bankruptcy. And we designed for them the Orpheus, this, and an active loudspeaker. And I can remember thinking to myself, and I turned to Alan and said, well, it's all very well being a consultant, but the reason that I'm being called in, you're fine, you do the appearance, but I'm being called in because these companies haven't done their R&D work, they haven't prepared the ground, they haven't got built-in engineering. And I just seem to be called in by flaky companies. And so, why don't we have a flaky company of our own? and that's how we started Meridian.
Right. Is it coincidental, by the way, that doesn't feature any sliders after the Lexon? I remember the sliders on the preamp being a source of concern.
They were a thing of the day, weren't they?
And so you started up Booth Roy Stuart Meridian in
1977,
and your first product was an active speaker, the M1.
The M1, which I couldn't find a picture of this morning when I was looking for one, but that was our first product.
And that brings us to the first topic area that we want to talk about, active speakers.
It cornered me.
Yes, sorry. It seems like an awful long time ago, but the point is it remains a valid topic, not only because you've built on the concept by putting DSP into them and feeding them with digital signals from 1988, I believe, your first product that did that.
Yeah. 1990.
Okay. I've seen 88 in some of the written material.
88 was the first digital speaker we did with a digital input, but it had an active crossover. But the first DSP crossover was actually done by Richard, who's sitting there, closely followed by Rhonda, in 1990.
Okay, fine.
Yeah.
So what makes this relevant today is that you're still ploughing a pretty lonely furrow as far as this is concerned, aren't you?
Well, you might think that, because people think that Meridian's the only company that makes digital speakers, but actually there is another company that makes lots of them. They just don't advertise. It's called B&O.
Okay.
Yeah.
But there's plenty of other people in the industry who have not followed.
Oh yeah, 99.9% speakers are not.
So tell us why they're wrong then, Bob, please.
Okay, should we do that?
Yeah.
Let's just go with this one.
Excuse me.
Yeah.
Can we turn those front lights off? We might have probably
Yeah. Tony? Hello? Is it feasible to turn these lights out at the front?
I don't know how to do it.
You still get a picture, in other words?
We-
Okay.
We can make a flying run through this, but
Leave it. We could try having them on further back. Do you want to experiment with it?
that's okay. You may remember that we were working with active speakers.
Is that better?
Yeah, not only at the Cambridge Tape Recording Society, but at the Oxford Tape Recording Society. So, went to all those years ago. Okay, let's. Are you doing that?
Dave at the back is. That's it. Full gain.
Okay. Well.
Just project your voice. Excuse me, saying
Yeah. Sorry, it's kind of difficult. I'm trying to look at the computer and also speak and the audience at the same time. Okay, I'll do that. Okay, so I've got some slides here which are based on a UK conference 2006, Audio in the Home. So if any of you are interested in following it up, this is actually published in the AES, Active Loudspeakers. I actually wrote it up after a while. And shall I just go through a bit?
Yes, do.
So at that time, the purpose of the lecture was to show why active speakers were 1,000 times better than passive designs. And just to set some of the background, there's a number of different kinds of active speakers. There's speakers with amplifiers in called powered, speakers that are equalized. But the ones that at Meridian, or as far as I'm concerned, the true active speaker is always got an electronic crossover of some form or another. In other words, it's got separate amplifier for different drive units. And a digital speaker is a particular class of active speakers. So if you look at this, the top shows the traditional way that speakers are still made. The majority of speakers are still made this way. It's insane, but there it is. You have a power amplifier with fixed gain, voltage source, lots of current capability, and then passive elements in the speaker to separate the frequency ranges. And the active speaker uses a separate power amplifier for each driver. It can be a two-way, three-way, whatever. The key point here is that the amplifier is directly connected, which has tremendous benefits. You get good electromagnetic damping of each driver. The power amplifier can be uniquely matched to the drive unit, both short, medium, and long-term thermal. Its frequency response can even be matched to it. And then the active crossover will always be better than the passive crossover because it's operating at low power with more ideal components, right? I probably have to go rather quickly through some of this,
Yes.
I think. But there are a number of things that we can do with the active electronics, including equalization, fixed or dynamic equalization, motional feedback, distortion correction, and so on, transducer protection, thermal compensation. Our current speakers work out continuously the temperature of the voice coil, each voice coil, to protect the speaker. Now, a general purpose amplifier tends to be quite a big thing with a large heatsink, a high current capability, like I mentioned. Things that could look like this. There's a 5-channel, amplifier that has to drive anything. And one of the problems in our world is that speakers, may normally be rated at 8 ohms, but to be a good amplifier, it has to be able to drive at least 4, maybe 2, sometimes 1 ohm. So there's a huge amount of over-engineering goes into the passive system simply because the passive crossover can be so malignant or the speaker itself could be badly designed. By contrast, that's what's going on.
Yeah.
By contrast, what this shows is a total electronics for a DSP loudspeaker of 5 power amplifiers and so on and so on. There it is. And a modern example of a small speaker could look like this. We have the amplifiers and the crossover and the DSP and the microcontroller all on board. Okay. What are the advantages of active speakers? Well, I've mentioned one, which is you have a low-level electronic crossover. You have a power amplifier directly connected to each driver. One of the first benefits that gives us is thermal. The power amplifiers can be much smaller than they would be to get the same volume of sound through a passively connected system. For example, if we do a division, let's say you want a 20-volt signal in the woofer and 20-volt signal in the tweeter, you can do that with two 25-watt amplifiers. In an active system, you need over 50 watts in a passive system. But even then, you've got it mismatched. This graph shows the way the power tends to be spread in a two-way system between the high and the low frequency. And at the bottom, we've got the frequency of the crossover. And each curve shows the peak and the 1 second and the 10-second moving power according to the crossover frequency. The peak power is important because we need the peak power. The 1 second tells us how the power supply has to be able to deliver instant current, and the 10-second tells us about heat. And what you see is that in an active system, although we need the peak power, we end up with amplifiers that thermally have much less to do. Up to a quarter or a fifth of the heat sinkings required. The transformers can be smaller. So you can come up with a very effective engineering solution in terms of power sharing. Or you can use the same size amplifier and it'll play louder, which is the other approach. Another thing we can do is to modify the frequency response of the speaker. Because if you design a passive speaker, you've got very severe numbers of constraints, not least of which is the drivers. Tweeter and mid and bass will have to be roughly the same sensitivity. The frequency response you get will be dependent pretty much on the cabinet. And this equation relates the efficiency, the volume of the box, and the 3 dB cutoff of a loudspeaker. It's a general equation which holds true. What this says to us is to play an octave lower, the speaker has to be either 8 times the volume or it has to be 1/8 of the efficiency. Generally speaking, people want to make speakers smaller and have lots of bass, so this equation is critical. That's it. Every octave requires 8 times the volume increase. Now, if you start with the simplest form of speaker, which is a closed box speaker, the frequency response will depend on the cue. Size of the magnet, volume of the cabinet, interact to give you the response. And there's a variety of responses. Nobody wants to live with the blue one. Lots of people would think the black one is very fast, but you get most extension with, with a cue of 1 or 0.7. One way to get more bass is to equalize it. So as soon as you break the rule and say, this speaker does not have to work with any amplifier, but we say this amplifier belongs to the speaker, and now we're going to change its frequency response of the amplifier, you can equalize it and get an extension of frequency response. So by putting more power capability into the amplifier, by equalizing it, we can gain extension. You have to put quite a bit of power in to get another octave, but it's completely doable. The blue curve is obviously the response of the equalizer. Theoretically, you could have a filter that goes down to DC, but you don't want to do that. Now, another thing, when you're designing a loudspeaker that's a passive, you have very limited choices about the magnet and the coil and so on. The BL factor is what we're talking about here. The stronger we make the magnet, the more efficient it'll be. So that the red one has got a stronger magnet, more output, but reduced bass response because we get more damping. With an active speaker, we can trade magnet for power. You can decide whether you want a system which is loosely damped with a smaller amplifier that's equalized, or an amplifier, with a larger amplifier, or one which is more damping and a smaller amplifier. And so you can see here that we can end up with this blue curve, the target frequency response, with any number of an infinite sizes of magnet and different power amplifiers. By using this technique, we can get a whole octave by increasing the power by probably a factor of 2. If we're prepared to have a frequency response that rolls off more steeply at the bottom, like this one, we use an auxiliary filter which boosts the bass but then cuts off. We can extend the bass with considerably reduced requirement of the amplifier. Now, what's interesting about this speaker is that it requires only half a dB more power level than the passive, and it's playing an octave lower. The average power will go up, but the peak power that's needed doesn't go up a great deal. Now, let's talk about closed box speakers. If you look at vented box speakers, speakers with ports, and by the way, there's a great paper on this by Neville Teal called Loudspeakers, Enclosures and Equalizers, which everybody should read. A vented box allows us to play the speaker lower at the expense of order, and we get reduced cone deflection near the port frequency, which is really good, and typically a 3 dB increase in efficiency. But the equalized vented box is very, very much better than the closed box. This graph shows the deflection with frequency of a closed box speaker. So at the port frequency, these are different orders. For B2, which is the closed box, at the 3 dB frequency, you've got the maximum cone excursion. Right? This is the B2, this is the closed box. The B4 reflex speaker has maximum deflection there. The vented box, which is shown as green, has minimum deflection at the 3 dB point, but then it goes out of control below the port frequency. And you often, if you look at a vented box speaker, you can see it gives a lot of bass, but then the cone could well be flapping, and that's because there's no damping of it at all below the port frequency. And the port frequency is, roughly speaking, the cutoff of the system. If we do B6 vented box, which is got a port and an auxiliary filter, we can control the peak deflection of the cone. And this table shows the amount of gain you can get in loudspeaker driver power handling capability with equalized ported loudspeakers. B2 is the closed box speaker, no advantage. B4, standard reflex speaker, 4.2, B4 as a vented speaker, 6.5 dB reduction in driver deflection, compared with 4 dB if it was a closed box equalized. Okay, that's the left column. B6 is 10 dBs better than the standard closed box. So it's 1/3 of the cone deflection. And the highest that we ever took it to, in fact, the first speaker we made, the M1, was a B12 system with a 14 dB driver noise deflection gain on a closed box speaker. Make enormous, prodigious amounts of bass, and the woofer hardly moved at all. So you get tremendous, improvement in power handling. I'm going to skip over the motion feedback because we haven't got enough time, I think. The other thing about an active speaker is that the crossover itself is electronic. So it can be designed to be arbitrarily complex as long as it's transparent, without any of the constraints of, damping or losses that you have with a passive crossover. You can do it time equalization, much higher order crossovers than one can do with the passive. This just shows the completely standard LR4 Linkwitz-Riley, which is in the literature. I'm not going to talk about types of crossovers because there's whole AES books about that. But the active one is obviously much, much easier to design well. And if you're smart with electronics, it'll sound clean and clear. Next thing about active speakers is equalization and power. I talked about that a little bit earlier on, but the crossover has a bearing on the power sharing between tweeter, mid and bass. And I've talked about the trade-off between the magnet and the amplifier and the heatsink and the box size. Typically we try to make a speaker small, but you can choose it any way you like. Generally speaking, we can have more extension if we put in a bit more power. We have a much smaller heatsink, and we can use stronger magnets to make a speaker which is much more optimized. And part of the whole point of what I'm trying to get through rather quickly is that the right way to design a speaker, in my opinion, is as a complete system. It's a synthesis, and it's much more efficient. For the same amount of amplification, we can get a much louder sound. We get really good clarity because each power amplifier is directly coupled to the driver, and so when the music stops, the driver stops. It hasn't got this weird passive crossover element getting in the way of the damping. And then, of course, with an active speaker, you can be much more flexible when it comes to the native driver response. You don't have to throw away power to equalize. In fact, it's better if the driver's natural response is not flat and it follows the spectrum of music. Because then when we equalize it to be flat, we're gaining power handling. Okay? Remember this? Peak levels in music. So the curves I drew, which shows how you equalize a speaker to play lower, could imply that you need enormous amounts of power at low frequencies to get the response. However, music is not uniform in power at all frequencies. And there's been a number of analyses. I mean, Adams, Sivian, Dunn and White go way back to there. They obviously, as you can see, in the 30s didn't have much bass and treble going on in their music. And as time's gone on, we tended to see more and more extended. The blue curve, by the way, is the AES standard noise curve that one is supposed to use for testing these things. But the spectral density, if you like, of music, it's got worse with time, or better, depending on your viewpoint. But nevertheless, you can see here that below 70 hertz, it's rolling off. So we can equalize the speaker below that frequency and not really need much more power, peak power, to deal with it. And at high frequencies, it obviously rolls off, but typically that's not a problem. And if you look at these specific recordings, that Keith and I exchanged a lot of notes about what's the worst recording for bass. This one, which is often used, Jennifer Warren's Way Down Deep, is probably as bad as it gets. You don't think so, do you?
I told you about a CD called The Bass Outlaws.
Yeah, the Bass Outlaws. It's just
Yeah,
really
but that's
bad.
not music, so you don't have to worry.
But even with these, the main point I'm trying to make is that at high frequencies there is not a lot of peak energy, of average energy, and at the bass below 80 hertz, energy rolls off, and so we can use boosting in that area, and it's very successful. That's how subwoofers can be built. Active subwoofers can be built because you can put a lot of equalization, boosting it towards the lower and lower frequencies, and not actually need to get in there. Although I have to confess, I didn't include dinosaur footprints in this analysis. So that's too complex to go through quickly. Yeah. What we're showing here is the peak and average power from some studies in a low frequency system, depending on the cutoff frequency. And Penkov, who Hungarian,
Don't know.
yes, wrote 3 very good papers in the AES journal. If you do a search for him online, analysis of music spectra. And Metallica was included because it's a bête noire of mine, heavy metal, which burns out tweeters. So the high frequency system, you'll see that with modern music, we need considerably more peak power and average power. You could need up to 10 watts now, mean power capability in a tweeter, whereas 15 years ago you could do 3 watts mean power capability.
The latest Metallica doesn't have that much dynamic range.
Well, they obviously listened to my complaint.
Yeah, they've gone down.
So, as you can see, there's a whole raft of reasons why an active speaker is just a well-engineered solution. We've got a separate amplifier for each driver. We've got the crossover itself. We can put the right amount of power. If we want to use the same voltage rails, you can change the impedance of the drivers to get a sensitivity match. You know, we have speakers with 15 ohm drivers and 3 ohm drivers and this sort of things because it all matches. You can make you can make it very efficient and play lower. And that's what people want. They want a speaker which is smaller, plays lower, and loud. And it's so much easier to do it with the active technology. Now, DSP, as I mentioned, is a class of active speakers, and it inherits all the benefits of active speakers with more, because by using DSP crossovers and signal processing, we can do things like linear phase filters that can't be achieved in the analog domain. You can do time alignment, time domain equalization, and of course we can introduce delays, arbitrary delays to line up the acoustic centers of each of the drive units in the speaker. So DSP has a tremendous benefit, and many more options for dynamic correction. For example, there is a class of speaker, typically a small speaker, where you can make it play to quite low frequencies when it's quiet, but as the louder it gets, you have to sort of modify the amount of bass that it's putting out. That sort of thing is very easy to do in DSP, and it's quite difficult to do as an analog circuit. So that can be done. And precise protection models. You can make a speaker that you cannot burn out by putting any signal into it, because it can easily calculate what's going on, and user controls. This is just one example. We can have very steep crossovers, almost arbitrarily steep, in an active speaker, in a DSP speaker. The other thing I mentioned, time domain equalization. So here's an example of the feeds in a two-way speaker, which you see this is the boost that's going on at the bottom end, and this is the frequency response coming out the amplifier with the DSP, which is correcting things that are going wrong in the drivers themselves. And we can improve an impulse response, say from this to something like this. So by doing that, you get more transparency. Now, another benefit of a DSP crossover is that all things being equal, well, first of all, you're taking a digital signal to the speaker, which means that you haven't got a preamp, and in my world, there's no preamp like no preamp. You don't have a cable, or an analog cable, it's the same thing applies. Taking the digital signal all the way in, splitting it, equalizing it, and we turn it to analog, in the case of our speakers anyway, right at the last minute, inside the speaker itself. And these are just some examples of what DSP electronics could look like. There's a very modern one. That's actually the three-way speaker from the inside of our table radio, the F80. So, actives are better. The optimum equalized vented box will extend the response by 1.5 octaves in a 16th of the volume of a closed box speaker with 16 times the efficiency, requiring 1 dB more power output. Driver deflection comes down by 12 dB. So if we put all that together, it comes to 1,006 times better, which was the point we're trying to prove. And as I said, this is, you can download this, I guess, or you may have it. And there's quite a lot of stuff in here. Actually, I read it again today. I thought, that's bloody good. I hadn't set it down before, but it goes through many more, and there's a lot of good references if you're interested in learning how to design a speaker. So that's the.
Thank you, Bob. Having
Lightning.
mentioned, yes, thanks for getting through that in such short order. Having mentioned the benefits of DSP, I know that you also have very strong views as to how DSP shouldn't be used, not to make a silk purse out of a sow's ear, for example. And that carries over into your views as to how it should be applied in room equalization as well. Perhaps you could talk about that shortly.
Just to say that the more powerful the tool you have, the more badly it can go wrong.
Mm-hmm.
Yeah. So and DSP is an enormously powerful tool, and the team, Rhonda does this, and her team, they do a fantastic job. But even the best people can slip up occasionally, and you have to be so careful with it because if the things that can go wrong in a completely different dimension from the other parts of loudspeaker design, for example. The main things are, you have to maintain transparency, have to maintain linearity in all the processing that's done. And it's
And do you have to know which things to correct and which to leave alone?
Yes, I think so. I think it's important that you don't correct things. Personally, I'm extremely reluctant to, for example, correct response deviations that are narrower than the bandwidth of the human, the auditory filter.
Sure.
Right. Okay. I think if you go narrower than the auditory filter, you're asking for trouble. And so some equalization systems, which do this very fine response stuff, end up sounding unnatural. There are certain kinds of defects that happen in audio products, and loudspeakers are really interesting. You can have a box, and the drivers have 5 or 10% distortion, but it's a kind of distortion. The amplifiers have, 0.01% of a different kind of distortion, and we can clearly hear an error that's introduced at the 22nd bit on a digital filter. And so you can't use numbers. It's horses for courses. You have to know which part of it you're tackling. So you asked about room correction.
Yes.
So I personally believe that, and we implemented this. Rhonda and is Michael not here, Rhonda? No. Produced the DSP equalization system, which operated on room modes. I think it's quite safe to equalize below 200 to 300 hertz, where rooms have primary modes and they can be removed. And it's quite treacherous to equalize above that. I believe that the speaker should be right. And if you try and equalize above that, you're very likely to be going to equalizing for reflections, off the edge of the speaker, or reflections of things in the room that will lead to smeared time domain information. The other thing is that I really passionately believe that the speaker should be in the same room as the listener. And by that I mean, when you're sitting, like we're sitting here and we talk to each other and I hear you directly, but your sound isn't equalized, so you speak to me and I immediately have a map of the room. And when I hear you somewhere else, you still sound like you. Or if you moved over there, you'd still sound like you, even though if we made a recording of it, which we are, you'd sound quite different in these different positions. If you equalize the speaker in the voice band and above, I think you're then putting the speaker almost in a different environment, and it becomes less natural. It'd be better to listen to the speaker in the room. And if there's a problem with the room, fix the room. If there's a problem with the speaker, get a proper one. You know. And yes, all rooms have low frequency modes, and they muddy the sound and they interfere with the, the timing and the tune and so on, and that's well worth doing. So our equalization system deals with room modes, and that's the limit.
Okay. Let's move on, Bob, because...
Sorry.
No, time is pressing. Let's move on to another topic entirely. You were, as a company, you were very early adopters of digital with the MCD and the MCD Pro players based on Philips machines. You went on to play a much more active role in the development of what was to follow, in the way of contributing to DVD-V having some proper audio provisions within the standard, and following on that, of course, DVD audio. And all this stirs in rather nicely to your long-standing interest in psychoacoustics and coding systems, the most efficient way to code what is required by the human hearing system in the way of bandwidth and noise. Talk us through your critical periods in your input. You became chairman of the ARA, and it was in that role really that you pushed the audio agenda to the DVD forum.
Raymond Cook gave me that chalice, and the ARA was quite an interesting group of thinkers, and included Michael Gerson, and I think you were involved, weren't you? Yeah, exactly. So we were trying to put together something that would give a better carrier for sound. And the reason I got passionately involved in it was that I could see with DVD we had room for enough data, maybe, to be able to put a recording on that had a big enough space to encompass everything that the human could hear. And so that with the 4 gigabytes and the higher data rates, we could do some things that were interesting. And the ARA, of course, it didn't actually begin there. It was all about surround sound. Decided to advocate this, and we had a Japanese division, chairman of which was Mike Suzuki, who later went on to become the chairman of WG4, and in the UK, Malcolm Hawksford, Tony Mears, Michael, so a whole bunch of people. We put together this proposal for a high-quality audio disc. Now, this is at the time when Philips were talking about MMCD. I don't know if you remember that. Yeah. And before, SD and MMCD had combined to be DVD. And we proposed lossless compression, higher sample rates, bigger bit depths, 2-layer disc, lots of things that were quite prescient. Why did I go advocate on it? Because I just thought it'd be really great if we could have something that was better than CD, and something where I could give back to the industry that was giving me my livelihood something worthwhile. That was really where it came from. And prior to that, we'd had a little organisation called Extra Bits, which comprised Peter Craven here and Michael Gerson and myself, and we were doing all sorts of things like buried data and different kinds of dithering. And Rhonda and I did a whole series of bits of work on noise shaping and dynamic range enhancement. But we knew then how much dynamic range was needed. Is that helpful?
Yes.
Do you want me to talk about it?
Yes, please.
I guess we'll take it from this point. Sorry. These slides are taken from another paper which got me into a lot of trouble, called Coding for High Resolution Audio Systems, that was published in the journal March 2004. Fortunately, I'd got my fellowship by then. And we'll talk about that later, I'm sure. But March 2004, if you would like to refer to some of these things, that's also in print. But what we were concerned, you want me to talk about this, or do you want me to talk about ARA?
No, talk about
This is
this.
fine, okay.
Absolutely.
Because ARA went on to DVD audio and SACD and that whole thing. We'll talk about that later?
Yeah.
Okay. The essential point we're trying to get across was high resolution. Not how do you use psychoacoustics to minimize the amount of information available so that it's not deteriorated to the point where you can't understand a phone call. A lot of psychoacoustics is about the minimum capability, or the minimum, at least in the literature at the time we were doing this. My interest has always been, how do you get high resolution? How do you get so much realism that you could believe you were there? And the key points, you know, high resolution are realism, transparency, is the sound immersive? One of the questions that I proposed in this paper was, what is the channel that could be between me and you now and you wouldn't hear the difference? So you can go to a live performance. What can we put between the performers and the listener so that you would not hear the difference? And there's two important reasons for that. You want that to be known, and you want that to be known for posterity, because an important aspect of recording, and Tony will, I'm sure, agree with this, is that you're laying down an archive for future generations. And the quality of the archive, which was something that Michael was passionate about, had to be transparent. So what is it that we can put between the listener and the event where there is no audible consequence, no risk of future detection? That is not the same thing as, you know, what can we get away with by gain riding and mixing and all these different techniques that can be used. This is an absolute search for transparency. And the model was looking at the reproducing chain in this way, that you capture recording, and this is your archive, this is the artifact. And then it's put on a carrier, and then it's played back. And the properties of each of these different boxes affect that. So there's a difference between transparency and losslessness, because lossless is the ultimate standard once you've coded it. You've got a piece of data and you can transfer that losslessly. But you may want to do processes, and processes can be audible. For example, equalization, quite audible, but the errors in that process shouldn't be. So even the concept of transparency can apply to an audible process. And lossy processes, where things go wrong, either deliberately or otherwise, tend to be characterized by modulation of the noise floor, or shaped noise floors, or at least signal correlated errors. I mean, signal correlated errors, we've all heard them from transformers, from tapes, and obviously from poorly dithered content, or undithered content. And so these things, I'm just trying to make the point that the transparency isn't always lossless. So there are several elements to a sound system, to a channel being transparent. One is how much dynamic range it will carry. How much dynamic range is actually needed to convey a sound that human can hear and the next generation can listen to, and we won't hear a defect in it. And what is that number for recording and mastering, and what's that number for distribution, and what's that number for playback? Because they shouldn't necessarily be the same thing. Now, all of you, I think, aware of the concept of dithered and undithered quantization. Every digital system has a quantizer. If you dither it correctly, it is perfectly linear, but we've introduced a noise. If we don't dither it, we have a distortion. And this is showing an undithered quantizer, high-level signal. As we come down, the error becomes more and more and more structured. Okay, so that's just basic digital audio. And here's the FFT of a very quiet 1 kilohertz tone, minus 90 dBFS. The black is dithered and the red is undithered. And you can see that the under the signal has lots of odd harmonic elements in it. In fact, an enormous amount of distortion in that. I can't remember exactly, 30 or 40%. In a digital channel, and let's take the CD channel, which is 16 bits, there is a dynamic range inherent in the 16 bits. And if it's properly dithered, it produces a noise floor. This graph shows the audible significance of white dither at the 16th bit. Now, the reason that the black curve is rising is that the auditory filters in the human ear get wider as frequency goes up. It's approximately third octave, but not exactly. It curls off down at the bottom. And you can see that if we said, in this case we postulated, set the volume control to the point where the loudest thing could be 114 dB SPL, which isn't, it's loud but not intolerable. It tells us that we can definitely hear a hiss from the dither. And you actually know that if you listen to any CD, you'll hear it. There's a significance to that. So 16 bits isn't enough, strictly speaking, to be transparent. We will hear the hiss on that channel if we turn it up to the point that the musical instruments are as loud as they were in real life. And if we accidentally have a dithering mistake and a truncation, a quantization in the channel, you see that the audible consequence of those harmonics is quite audible. It's well above the hearing threshold. This blue line is the average human hearing threshold. And this to a large extent explains why early digital recordings were criticized as sounding bright and grainy, because this kind of distortion existed. You all right?
Yeah, fine.
And as a historical reference, this shows the minus 90 dB tone with its harmonics in a digital channel, the sort of early generation CD, and the silent groove of an LP, audible significance. You see this LP has got this lovely warm, fuzzy, rumbly stuff going on at the bottom. And the digital channel, which has a much wider dynamic range, nevertheless was inclined to these kind of artifacts. So how much dynamic range we need? Is it 16 bits, 18 bits, 20 bits, and so on? And if you look at this plot, and this time we're referencing to 120 dB, so I'm allowing you now to sit close to the instrument. What channel will convey that signal that you're hearing? And you can see from this that 20 bits is the first time that we get below the human hearing threshold. Now obviously, when it's loud, it's not a problem. But when it stops, so you're in the hall, music stops, can you hear the hiss of the channel? The answer is, if it's 20 bits, you can't. And we've proven this. If it's 24 bits, it's ludicrously overspecified. But you may want that certain times of the chain. If it's 16 bits, not enough. Apologies to Boston. And with a 20-bit channel, you can actually do a number of signal processing events with the dither, you re-dither, re-quantize, and the noise power adds up, and it only just reaches the threshold. So 20 bits, theoretically would be okay. And the ARA said 20 bits was the minimum channel. And if you make mistakes in your signal processing and have an undithered quantization, it's very significant, 16-bit, and you probably get away with it at 20, and you absolutely get away with it in a 24-bit channel. Okay, so now if we look at room spectra and hearing thresholds, what is room noise like? Well, there's two data from Lewis Fielder's paper in the journal. I can't remember exactly when that was, but if you look at Lewis Fielder, he'll show you some data that was gathered of average rooms and quiet rooms. And it's a very quiet room that takes us below the human hearing threshold, but they do exist. And you can see here how the spectrum of room noise, broadly speaking, ends up around the 20-bit level. Obviously, in this case, even 16-bit errors would be heard in an average room. And we know that because we hear them. The next set of slides I'm going to show you transform the way we're going to look at this. So in this case, the noise signals have been processed to measure the audible significance to the human. In these cases, based on auditory modelling, we're changing the human hearing threshold so that we can represent everything in Shannon space. So that Shannon space is just dB versus frequency, noise spectra. And you see here the bottom line is a noise spectrum which is uniformly audible. In other words, this is the noise spectrum which, when we bring it up, is inaudible, and then at a certain point it becomes audible at all frequencies simultaneously, from low to high. It's a very special shaped noise called uniformly exciting noise at threshold, and it produces the minimum audible field. In fact, this is part of the process that produces the hearing threshold in the first place. Some of it's mechanical, low frequency, but the fact that there is this noise going on in the neural system creates the threshold. The hearing threshold is the most obvious nonlinearity of our hearing system. Now, if we put the human hearing noise spectrum on Shannon space, it looks a bit like this. And then here, in green, is the coding channel for CD. So this is the capacity of CD. There's an area here that theoretically it can't cover. High SPLs in the region up to 25 kilohertz. And there's a region here that we've talked about before that it can't cover. And 9624 is kind of ludicrously overspecified coding space for things that the human can hear. And 5211, nobody ever made one of those, is the space, the rectangular coding area that has the same area as the human hearing system. So if we were to use an optimum noise shaping system, we could use an 11-bit channel with the right noise shaping, 52 kilohertz sampling rate. It would encode everything we can hear. That's the basic thesis of that model. Now, if we look at not only room noise, but noise in recordings, we analysed quite a lot of high-resolution recordings. This is what we tended to find. Some tape hiss. The average ones were like this, but the minimum really quiet ones were like this. So the noise in the recording itself can be always above the 16-bit level, I think. Yes, that's right. And the thermal limit shown here is the limit for a microphone. Microphone can't be quieter than this due to Brownian motion. So recordings tend to be noisier, but that doesn't mean that you can't hear the noise that's introduced by the channel. Like I mentioned before, there's an area at the top where theoretically CD doesn't quite make it. There's this existence area of about 120 dB at 24 kilohertz that theoretically can't be carried by the channel, but I don't know any content remotely like that. You would definitely have to leave the room and the tweeter would melt. Probably the worst instruments for high frequency energy are the percussive ones, particularly cymbal. If you're very close in to something like a triangle, you get a lot of high frequency energy. But this is the spectrum of a cymbal crash, which is a very famous cymbal crash that allowed us to win the competition for lossless coding at DVD audio. And you'll see that there's an enormous amount of supersonic energy there. But when we set this at a normal playback level, worst possible signal almost for high frequencies, you see that actually at 20 kilohertz it's 60 dB SPL, which means that it's not 120 dB SPL. And therefore, the almost for the worst thing that we could find as a recording, there was no real argument to convey much above 20 kilohertz in the sound itself. It's quite interesting. And the 9624 space is really quite big, but that's the significance of this to us was that, or to me, was that it seems that the preference for high sample rates which we have, was probably not based on air content, but on something else. Higher sample rates are preferred because the method of bandwidth reduction is important, whether it's the way it affects time resolution or because of aliasing. There's tremendous capability in that symbol crash if you don't have good anti-aliasing filters to have content come back. But I believe that the reason that we've preferred sample rates higher than 44.1 is that the way the bandwidth has been restricted has been problematic, right? From the second generation of CD equipment and from the first generation of Philips equipment, A to D converters, D to A converters used brick wall filters which were built using FIR constructions. So the anti-alias, anti-imaging filters tended to have this kind of time response. And there's two typical filters shown here. The top one is 44 kilohertz and the bottom one is 96 kilohertz. And this is a very unnatural filter. All the filters I talked to you about in digital speakers, active speakers, they're causal. The FIR filter produces an output before the main event arrives. You see, with this pre-ringing which happens. So if the impulse is this energy here, the output starts to happen in advance. Yeah. Having got to the point where we thought, well, okay, maybe it's not the high frequency content that's causing us to want high sample rates. And there are many reasons why we know this is the case. Because, for example, I'm going to get slayed for this now. You can hear the difference between sample rates when the tweeter stops at 18 kilohertz. People can hear the difference in sample rates when they can't hear above 17 kilohertz. Okay? So, and yet, you go from 48 to 96, or 44 to 88, and there's a very obvious difference. You're just not allowed to write it in the AES journal. Get slapped if you talk about sound quality. But nevertheless, we hear these things, and the difference between high sample rates and low sample rates, the quality difference is everywhere. And so we thought that, okay, well, the next thing is we've looked at the energy, we've looked at the dynamic range. What does the frequency range have to be? Got it, it's 20 kilohertz. How do we get a channel that doesn't suffer from this defect? Gives us the advantages of what we hear with high sample rates. And at Meridian, we commissioned Peter Craven to do a piece of work on what I think he called apodizing filters. What we wanted was to say, well, okay, if we're going at higher sample rates, we don't have to use this kind of filter. We could use a minimum phase filter. We could use a filter that rolls off more gently, because we're not really worried about what's between 24 kilohertz and 48 kilohertz or 96 kilohertz. Roll it off more gently, that might be better. And we try it. And Peter came up with a great paper with a typical Craven title called Controlled Pre-Response Anti-Aliasing Filters. And that was in a convention 2003 March. Right? It's worth reading. The essence of these filters is that there are two things. One is it doesn't have a pre-response. It's a minimum phase. It rolls off more gently, but it has a null here, close to the Nyquist frequency. Now, the reason that's a good thing to do is that that's going to kill the ringing from the A to D converter, even if it wasn't designed properly. So things happen earlier in the channel, A to D, or even in signal processing, could have this pre-ringing type impulse response. But the apodizing filter nails it. And so, ideally it has a zero in this sort of region. this kind of filter then has an impulse response which is much closer to what we would call a proper analog filter. So here's an apodizing filter for 192 compared to a Butterworth filter. Right. No pre-response, all the energy arrives in pretty much in one go. And the ringing there is within a time domain that is definitely masked by the human hearing system. The reason we really went for this was that you can hear something and you have to try and explain why you can hear it. The sound of this kind of filter is completely different to a conventional linear phase filter which has pre-ringing. The way we use it at Meridian is we upsample, so that you take a CD and it's upsampled to 8824, but we apply an apodizing filter. And the other reason that's important is that most equipment these days uses integrated circuit D2A converters. It's very, very difficult and quite unusual to actually build your D2A converter from scratch. Nobody really wants to do that. So if you've got a converter element, it could easily have an FIR filter in it, and the apodizing filter simply stops that being excited. So we get more out of the DAC. We can clean up what happened at the recording and have a playback system that doesn't have a pre-response. When you hear it, it has all the advantages of high rate, but it doesn't have any of the energy at high frequency. So I wouldn't say it's proved the case. It's, to my satisfaction, it's worked. And these kind of filters obviously can appear in a 24-bit channel. There's 24 bits all the way through. That's fine, but that gives you a very inefficient transmission. Another way of improving a channel is to use noise shaping. Do you have time for this?
No.
No.
No, we've got time for other things.
Read it in the paper. Peter Craven and Michael proposed a really interesting equalization system. I don't have a slide of it here. Okay. Which used a particular pre-emphasis for high frequencies, for high sample rates, pre-emphasis and a noise shaper, which gives a tremendously efficient coding space. We can transmit everything a human can hear down a 10-bit channel, bandwidth with the right impulse response and so on. So anyway, this is the way psychoacoustics gets applied to digital audio.
Sure. Just to clarify, in case some of the audience didn't, because there was a mixture there of anti-alias filtering and reconstruction filtering. Your latest 808.2 signature reference CD player.
Got all of those.
Yes, uses a minimum phase reconstruction filter.
Yeah.
So effectively, we've gone back right to the early days of digital audio when these filters were realized with analog networks.
Yes, but it uses it after it's been upsampled to 88.
Sure, I understand that.
Yeah.
I'm not the only one I know, because I've talked to other people who are interested in how you went about designing that filter, and Rhonda hasn't told me very much about it so far, so I'm asking you. Clearly you've either made the calculation that the pre-response is worse than the sound of the phase distortion, or you've decided actually that the phase distortion isn't audible at all.
I'll tell you some of it, but I won't tell you all of it.
Okay.
One of the things we did to understand this was to teach ourselves what it sounded like. Now, what I find with audio is I think I mentioned it before, is that many of the defects or the things you're listening to are in completely different dimensions or different places to each other. So you can have a system which, with lots of warts, but you could focus in on one particular aspect. And in order to do this, what we did was build a set of filters. Rhonda did this so that we could teach ourselves what the pre-ringing sounded like.
Okay.
And the most obvious thing was the maximum phase filter, which was all pre-ringing.
Yes.
Right? And then sit down and do a listening test. You listen to it, what impact does this have on the sound? And it's absolutely fascinating. You immediately hear all the things that CD was criticised for, this glassy, bright, jangly thing, but also, quite interesting, we found a sort of, the best way to describe it, for example, you could be listening to a recording of a choir in a chapel, and it's almost like when there's a significant pre-ringing, you hear the music, but on top of it, you hear this kind of phosphorescence. It's the only way to describe it. It's like, the visual analogy is like sparkles going on in the air, which are, I suppose they're related, but the way you put it together when you hear we tend to separate the music from these things that don't belong to it, so they become disconnected. And so we trained ourselves what it sounded like, and then we did listening tests on, I can't remember, a dozen more filters. Yes, they're apodizing filters, but they had other parameters we were messing with, which we're not going to talk about. Okay. But the final filter was chosen by listening. Extended listening. And some of them, which measured almost the same, sounded quite different, didn't they? And so you have to be...
For reasons that you think you understand now?
Yeah,
okay.
to a degree. And I remember Rhonda being very cross because the one we picked was the one that needed the most MIPS. Right? I don't think we can turn the clock up that far, Bob. She said. Well, you have to, because it's anyway. So it's we did it by listening, and that's kind of odd. I think it's important to be humble enough to know that you can apply all the science you can, but we do not understand how the human hearing system works well enough to prescribe something, and so in the end you have to taste it. Yeah.
Okay.
So I shouldn't say go on saying N, should it?
I'd like to, we've got to leave enough time for questions from the floor. So I want to talk about your vision for where high quality audio is going in the 21st century, but I'd like you to stir in one of the other topics that we had written down but we haven't got time to deal with in great deal, which is multi-channel audio. You had an initial interest, I know, in multi-channel in the 70s, but effectively decided that so long as we were restricted to LP that it was never going to be a flyer. Became interested in it again as a result of digital audio becoming a reality, and the ARA, as you said, was formed principally at the outset anyway to promote multi-channel audio.
Yes.
Can you stir that into your vision of where audio is going, and the other factors I'd like you to consider are whether physical media are the way that we're going to be getting music in future, or whether recent experiences with DVD-A and SACD have dealt a death blow to that, and that we'll be downloading high-res audio in future?
The answer is yes.
Okay.
We'll do that. One of the more interesting things in my career has been what I call political engineering. The whole format thing was fascinating. You know, the idea that we could develop a coding system and go in and work with these huge companies. Often enjoyed the fact that we could sit at the table, and Meridian has one vote, and Pioneer has one vote, and JVC has one vote, Sony has one vote, and it's kind of surreal. The format making thing is desperate. When CD came out, there was two companies, Focused Idea, did it, right? And most things that are good in engineering are done by a small number of minds. And as we got to the DVD forum, you started to have these large meetings, and the format collected features. That then spawned into DVD audio and SACD, and as those formats were being made, the two groups were in competition with each other. So every time one group added a feature, the other one added it, right? And multi-channel was one of these things where the music industry said, we can't sell enough of our discs, so we've got to make it more interesting. Let's have menus and surround sound, Meanwhile, the audio people are saying, well, actually, surround sound's very good because it gives you this sense of immersion and it's better. But there are so many different vested interests come to format making that DVD audio and SACD became really quite incredibly complicated. And the fact that there's a format war is a disaster. format wars should be somehow banned in engineering. And every time you've seen it happen with VHS beta, you know, somebody loses out, L cassette, DAT, you know, all these things. So the format wars are treacherous, and I think it was Philips who said that by 2020 the latest format would last long enough to play one record. because there were so many formats that evolved, and DVD audio and SACD, we had all these meetings. You've got the music industry with their vested interests, you've got copy protection, surround sound menus, people with patents. It really quite horrendous process, and I've recently read the book about the American HD TV, and it's kind of similar, that whole thing. DVD audio and SACD had a battle, and the iPod won. And DVD-A was a fantastic format, but because there's a war, the studios wouldn't get behind either one. They wouldn't create the content, and there has to be content. And formats will only survive if there is a lot of content. The fascinating thing about CD was it was good enough for the man in the street, and if you really work at it, you can make a playback system that's really spectacular. But we can only do that because millions of people are buying the discs and sticking them in very ordinary players. And it creates a market for the disc, and so the content providers can make the discs and sell them. And then the catalogue becomes rich, and then the format stays. And with DVD audio and SACD, there was never this commitment to content, and without the content, it's dead. And the whole thing is very much worse. You know, when these committees said, ooh, let's make a bigger committee and do Blu-ray and, you know, HD DVD. I was in meetings with 150 people from Microsoft, HP, Dell, and so on and so on, all talking about, well, the customer's not going to like the ordinary disc. I mean, DVD is great because it's got good sound and picture, but the customer wants internet access, and the customer wants downloadable features, and the customer wants Java. And the customer, I stood up and said, guys, can we pay more and just have a thing where you press play and the movie happens? Because it was just incredibly complicated. Completely out of touch. When you look at the consumer analysis of why DVD was popular, it was two things. Top of the list, you didn't have to rewind it at the end, right? Nothing to do with sound quality or picture quality. Sound quality actually was way at the bottom, that it was better. Picture quality, you could pause it. That's one of the great things of CD. So there's been a tremendous disconnect, I think, in our world recently between people making formats and the people who actually might want to buy them. And I certainly think that we've seen it happen. I mean, the iPod won that battle. There is more and more and more high-quality download becoming available. DRM is collapsing. And with movies, people, I think the word is consume movies differently from music. With a piece of music, you can listen to it 100 times, your favourite piece of music, play it again and again and again. How many times do you watch a movie 100 times? The answer is, your favourite movie you might watch 7 times, but most films you watch once and think, wish I hadn't done that. so movies are even more important for a download model. You know, things like Netflix and so on. You can rent it. So but nevertheless, you know, we went in there and we said, if you're going to have this thing, it's got to have great sound quality, 8 channels, 192, 24-bit. We put in a stealth thing in Blu-ray, having learned a few tricks at DVD audio of how to get features, because one of the biggest problems with DVD audio was you couldn't play it back without a screen, right? But if it's a music disc, you really want to put it in, press play and enjoy it. And there was no alternate navigation for DVD, and there was no alternate navigation for DVD audio. So we said in Blu-ray, went straight for the Californians and said, blind people have to be able to operate the Blue Disc. So we did a paper on Blu-ray for the visually challenged and got the navigation points into Blu-ray. So anyway. Now, as to surround sound is it can be much more realistic, especially if we introduce the element of height. And we
Yeah.
enjoyed ambisonics way back. It is quite difficult to sell to the consumer, or if you sell it to the consumers, the implementations can be quite poor. And although we think surround sound is absolutely the way, and we should be archiving the recordings that way, it's very, very difficult to get people excited about putting enough good speakers in their living space to build a market. You can put out nice discs on DVD, video, but not many people have. You can put out nice discs on Blu-ray. You can put out spectacular discs on Blu-ray, and maybe there'll be one or two. The problem with all these formats, especially as it's gone on from DVD, you remember DVD has MPEG audio specified for Europe, and yet there's never been a disc made. And there is so much... One, the test disc.
I know, there's 12 monkeys.
12 monkeys, and the test disc that everybody has to use to test every player they make from now on, forever. So it's really quite a problem. Now, what was the other part of the question?
But no, you covered it with talking about multi-channel and the height element in particular. Do you foresee? I mean, if you accept that
I think height's incredibly important.
Yes. Yeah. Is it your opinion? I know it's Peter's opinion. He's expressed it to me that actually it's more important than the 360-degree horizontal. That the height is more important than the back channels, effectively. Do you feel that?
Yeah. I think it probably is. There's been a number of ways in which it's been done. Periphony was one. The German company that did 2 + 2 + 2.
Yeah. MDG.
And Divox, the Swiss company. Some of those recordings are absolutely beautiful, where you have a height element in it. And yeah, I think that if we could introduce height, because it's part of when you get a good surround system, it's just like instead of standing at the door and listening, you stepped in. And this is the key to it.
If we accept that the key problem to this is the implementation issue, then it's the hardware that people have to put in their homes that really puts them off. Do you see any technological solutions to that could lessen that hardware burden and make it more domestically acceptable?
One of the biggest problems that we have is the rear channels. And it is obviously the case that 2 good speakers are much better than 5 nasty ones. Yeah. And the surround speakers are hard to place often. So introducing height in the front image, I think, is the kind of thing that not only would give us better sound, but could be more acceptable.
Okay.
Yeah.
Is anybody working towards that, as far as you know?
Well, I wouldn't know if I told you I'd have to shoot you.
Okay. Bob, as I said, we have to leave time for questions from the floor, which there are going to be lots of, I'm sure. But I'd like to close on a personal question, if I may. I couldn't help noticing when I looked at your biography that you were born in 1948, which means you're 60 this year.
Exactly.
For all of those of us who cherish your contribution to the audio industry, can you reassure us that you're not about to retire soon?
No, absolutely not. I feel just as young as ever. Tony's here. He's part of the AES. Good heavens, he'll tell you about that. So 60 is just young, you know.
You're 40, Bob.
Then you're 40. You're as old as you feel, right? And that's I just love what I do and no intention of stopping. I'm going to go on boring you forever. So.
Excellent. Well, Bob, before we throw it open, I'd like to thank you very much. I think it went quite well. Thank you. Come on, hands up, please. And please speak into the microphone so everybody can
All right.
hear.
I'm Anthony Walder and I used to work for Cadec Electronics in live sound. You've covered so many really interesting things tonight. I've got 79 questions and I can't remember any of them now because I'm even older than 60. But the really interesting point that you made tonight was finishing a design by listening. Yeah. And that's what I've been doing for 20 years and I'm absolutely... But it only works if you're interested in high performance. And most people, regrettably, are not. But that is, sorry.
Yeah, you do have to have done the measurements beforehand, so you're not wasting your time.
Absolutely.
But then, absolutely.
Yeah.
And listening. You know, I gave a lecture at the AES in Cambridge where I said that one of the most important pieces of an audio engineer's toolkit is concert tickets. And, you know, go and listen to live music because it's all about reproducing the original.
Yeah, Bob, this is something you might agree with because we didn't touch on well, you mentioned in passing the issue of the recent paper in the journal about 16-bit 44.1 being enough. You mentioned that in passing.
Yeah, we have to cover this.
I was going to ask a more general question rather than talk about that paper.
No, I agree,
particularly. When you read scientific papers, we're talking about listening tests here, when you read scientific papers that have to have a subjective element in them, so you are judging the importance of a particular character, a particular feature, a particular non-linearity or something like that, the assumption is always inherent in it that the people who were doing the listening were listening to a system that was making good sound, that a system that was capable of revealing what it is you're looking at. Do you think, I suspect in many cases they're actually not looking to the best systems. They're not listening to the best system.
Maybe not, but also if you know the system, you can hear things through it. And sometimes it takes a long time, and that's one of the really interesting things. Is sometimes you can put something together, and you think that's good, and it's only after listening to it for a few days you begin to think something not right here.
Yeah.
And that, of course, that completely disappears in any sort of A/B test.
Of course.
Yeah.
Yes.
And part of sorry, go.
I'm sorry to interject, but it's on the same side. So what does that do for double-blind listening tests?
You know, those kind of tests are used a lot in psychoacoustics when you're trying to measure the capability of the hearing system in response to certain kinds of stimuli. Try to know how the outer ear works, how the inner ear works. As soon as you get from perception to cognition, it becomes different. So, do I have a slide on this? I think I might do. Let me just. You know, this is like how we work and how we live. We live by perceiving, and when we listen, when we hear things in real life, we don't hear tones, hisses, and pops and clicks. Sound comes into our ears, and the brain analyzes it immediately, externalizes it into objects. You hear a cat or a dog, or a violin, piano, at various levels. The problem with ABX testing is it can disconnect you from some of the really important things that are continuous in listening to music or listening to sound. Sorry, I don't. This was an interesting slide I just wanted to put up because one of the things that happened to me when I came into the audio industry was I was, as I said, hauled up on the map many times by Peter Walker and Peter Baxter, who I highly respected, and, loved to death. But if you can't measure it, you can't hear it. And I think that's potentially arrogant. I think you need to measure what you can, but then you need to ask yourself some questions. So, for example, the violin maker never expects two of his violins to sound the same. Why would I expect two loudspeakers to sound the same? So, there are going to be things that are different. We use these natural materials. And we use them to make cabinets, and even the same design can sound different from unit to unit. I'm trying to get to a slide that is about this topic. Sorry about this. The point of this slide was to say, what is that, You have no idea by looking at it. So that's one way of measuring it. But when you hear the first bar, you would know that it was a bridge piano trio. And as soon as you heard it, you'll map the room and you'll say the instruments are here and it's this kind of instrument. And we're hearing very complicated things. And these things involve memory. Memory of what it is for recognition, and memory that once heard means that the ABX test is going to fail. Because you can listen to A and hear a defect, something's missing. You hear B and it's there. Go back to A and you hear it again. So here we are. So the perception of objects. All these different factors lead to the perception of objects. And the clearer the signal, the clearer the perception we will make of it. You know, this is like saying as signal to noise ratio gets better, we have a better and better idea of what it is we're listening to. And I've got a slide, I've got a simulation that many of you will have seen from me before. I'm going to put up again because I think it's really important. As the signal to noise ratio improves, we hear more and more. One example I well remember, and Richard is here in the audience, he and I worked on early CD players, and we made an improvement to a player, and suddenly we realized that in this recording, there wasn't one guitar, but there was two guitars. And then having heard that, on any system from then on, you can hear the two guitars, yeah. Right? And it's the human hearing system is not linear, and our perception system is not linear. So this is an image, you know, where the signal to noise ratio is improved progressively. And some of you have seen it before, but can you see what this is? See when it comes up next time, so it's going backwards and forwards. But once you've seen it, you continue to see it. So here is a Dalmatian dog with its legs and so on. And having seen it, having perceived it, you'll continue to see it. This is exactly what goes on in hearing, because there may be a click in a recording or something like that, and once you've heard it, it's always there. And yet, in an A/B test, you could easily lose that or miss the significance of it. And in terms of music, quite often, what we feel about, what we connect to emotionally, takes a long time to dial into. I'm sure you agree, Martin. You listen to something and maybe it's after several minutes that you either hear defects or things in the recording. So ABX testing, I think, is very, very good for what it's for, but it is seriously flawed for at least that reason, and there are other reasons. Human hearing system is non-linear. We concentrate on certain things. You know what it's like. You can go to a performance and decide you want to listen to the flute, and you look at the flute, and you hear the flute, you're paying attention to it. And the application of attention to one of the strings in the overall means that you can't repeat this. The idea that of an ABX test, it implies that I'm a black box and that I'm going to work the same way every time, and I'm not. Actually, I can't. Yeah? So it's a long-winded way of saying that it's of dubious interest.
Michael Page from PV Research. You make a completely compelling case for the superiority of active loudspeakers, and the market in professional studio loudspeakers would seem to vindicate your position. That said, why is it then that in consumer electronics, in hi-fi, there are so few people doing it?
You know, there is an established situation where people have amplifiers and speakers and they change them. The truth is that almost anybody with a garage and a saw can make a loudspeaker. And at least when we came into the business, it was very rare to have all the skills under one roof, to be able to do the electronic design, the amplifier design, the speaker design, and the persistent pig-headedness to try and sell it to the market. These days there are many more active systems. There are. And as engineers, we all know that's the right way to do it.
It's not quite true, though, that there are so few active
systems. It's simply in this rather rarefied hi-fi scene that it's so frequent. Because you walk into PC World,
Exactly.
every speaker in there is active of a sort.
Yeah, exactly.
Just
No, it's much more
designed
common.
down to a price.
That's what I said earlier. I mean, this is much more common now. Speakers like that, there's lots in the pro area. It's more usual to be powered than not, I think.
You described the audible difference between the filters with lots of pre-ringing and no pre-ringing. I'm guessing most of that energy is above 20 kilohertz. So I'd be interested to hear your thoughts on how that becomes audible.
The only explanation can be that we hear the wavefront.
Yeah.
We hear the wavefront and we hear the smearing of the timing. The binaural hearing system is capable of resolving time differences down to about 30 microseconds. So I think it's in this area. Yes, you said, I don't think you're hearing that ring. You're not. But you're hearing the consequence of it. The wavefront arriving sooner or being smirked, being blurred.
Can I just make you say your DSP use high order filters in the crossover. Problem is that doesn't take into account the polar response of the two units, for example, if you're using a 2-unit system.
That's correct, but it doesn't.
That is one of the, I think it's one of the snags of using very high order filters in crossovers.
I don't think the higher order makes it any worse. I mean, the polar response of the drivers.
Yeah, but life's a compromise, and I think sometimes it's better to have.
The narrower the crossover, the smaller range at which you're going to have problems. You'd have less.
But it's also it occurs where the hearing is at most sensitive when you're talking about 3 kilohertz, 1 kilohertz, 2 kilohertz. It's a very critical frequency.
Well, the whole business of a multi-way speaker is a horrendous compromise. And you're always, the number of ways you have allow you to have a better and better off-axis response and reverberant field response. The narrower the crossover, the less disturbance there is in the total room energy. But one of the real advantages of the steep crossover is that you can get really good control of the tweeter. The tweeter is not moving as much.
No, I agree with you on that.
So it's a whole sort of total thing. There's no crossover like no crossover. If you could have a driver with the right polar response and no crossover, it would be even better. Yep.
A question on the, or at least a comment plus question on the surround sound thing. It seems to me that many years ago when I was probably went to sleep for a long weekend, and when I woke up I realized that the professional audio industry had lost control of its destiny. We had effectively been reduced to picking up the crumbs from the computer and video people's tables. And whatever we did had to fit in with what they wanted to do because they were controlling the market. And it seems to me that the surround systems that we've heard are based upon war and disaster movies and such like, which Hollywood wanted to impress us with. And I have become so dispirited over the years going to AES conventions and hearing various surround demonstrations, not one of which has approached the periphonic demonstration in the old APRS show at Olympia.
Yeah.
And I just feel that we have lost this. Now, how we can possibly get it back so that music actually gets the format which it really deserves, as opposed to Hollywood, I wonder if you can see a possibility of this, and if so, how?
Hollywood strongly advocated for sound on DVD and HD DVD and Blu-ray, and the problem that we had with surround sound all the time was that the format was a video format, and the only way you could persuade families to put speakers in their homes was to watch movies, and we had to comply with this 5.1 format. So then the music industry was left to solve the problem of how do you make a recording that will work in a theatrical layout. which is definitely not the way to start. It absolutely deserves periphery and, you know, the same speakers all around. But there's very little interest in it. You know, we're excited about it. You try talking to the music industry about it. All they want to know is about how they can sell more downloads. And when you say about height, I remember having that conversation with the people at Warner Music. I said, DVD audio must have a height channel. He said, don't be so silly. You know, young man at the time. We're not going to do that. We're not going to stick up any more microphones. Every channel that costs a lot more to do. And so on and so on. But we did put it in Blu-ray. There's a flag for periphery, isn't there? Yeah. But
I think
no one's really going to make the recordings. That's the problem.
I think the biggest market for surround sound is basically classical music, where you're trying to sort of reproduce a real-world reference point, like an acoustic, and it's great for that. But I think, unfortunately, most people that consume music these days and buy music are teenagers who listen to pop and rock music.
Yeah.
And the pop and rock industry seems largely to have ignored surround sound because, and I can understand the reasons why, because its use is normally very gimmicky and people are not interested.
It's all about radio play, it's about download, it's about iPod, it's 2-channel, maximally compressed. The good news about download and iPod is it gets people interested in music.
But
in terms of reality recordings, a well-done paraphonic recording or a good surround recording can be superb. But there is another way to use multi-channel that I thought was quite interesting, which was espoused by Tacit, where instead of saying, well, we're going to take you to the concert hall and put it all around you, so we're going to take you into the performance and actually have the performers around you like you were one of them. And that use of surround sound gives you incredible insight into the music. So it's, anyway, but a lot of these things were dismissed as gimmick. So.
I think there's actually opportunities for every possible way of using surround sound. When Ambisonics was first being developed, I was one of the people who was saying, this is a very nice microphone, thank you very much, but I want to mix multi-track rock music with it. And I've always found it extremely useful to, and people do want gimmicks and they do want stuff going on and what have you, and surround sound is a wonderful gimmick if you can sell it properly. I think personally that the ultimate answer, which is something we've been chasing for years and years and years, is the idea of essentially doing the audio equivalent of a PostScript file, and what you get at the end depends on the resolution of your output device. If it's got lots of channels, then you can have periphery, and if it's got no channels at all, then you can have mono, and all sorts of things in between. And I think also that every type of music and every type of recording technique has those possibilities. I don't think it's just limited to trying to recapture a live event, because 99.995% of all music that's produced is at the live event. The original sound is what the production team listen to in the studio and say, that's the master.
Well, the main thing is you've got to have the channel, the carrier to take it to the customer. With Blu-ray, what we managed to do, by stealth, I think, was to put flags in the codec so that you could light up any of the 21 speakers of the D cinema array, which allows you, the voice of God and the speakers up high and the speakers down low. So you can do that if you want. You can do it high resolution. There's only 8 transmission channels on the disc, but there are flags for hierarchical processing. And the thing that Michael did, the hierarchical thing, was so you can have a multi-channel recording and you can play it back on as few speakers as you want. The information is all in there, and that's that's in the format. But we haven't been able to get any music companies remotely interested. Because what are they going to do? In reality, they're going to sell 1,000 discs to audiophiles, and you can't make a business out of it. That's the problem. That is the problem. There isn't actually. There's more interest in music. There's more interest in consuming volume of music, but there isn't interest, that we see. It's not that I'm jaded. It's just, intrigued, because it can be better. But Without software, it's a disaster.
Yeah, Tony Griffiths.
Tony.
Couple of points, Bob. The
ARA member.
The ARA member, yeah. Well, 3 points actually. Going back to those days, I admire you for your sticking into the standards business, because one of my last involvements was a trip to Japan to try and promote 5.1 as the standard when they wanted 4 loudspeakers, 1 in each corner of the room, and they had to be terribly tiny because Japanese rooms are very small. Yeah. And I gave a presentation to a committee of about, I don't know, 30, 40 people maybe. Mostly software, but software with hardware relations and so on. And at the end of the meeting, they conned onto the idea and they more or less agreed it. Unfortunately, when I arrived at the meeting the next day, the chairman said, "Oh, it's a great pity, we're not allowed to change this specification." So what the hell was going on here? And there's a man sitting next to me from a record company and hardware company whose name I don't mention, who didn't even belong to the committee. And I said, "What on earth is he doing there?" "Oh, he's flown overnight from Tokyo." Because I was there putting this 5.1 through.
Yeah.
And they just turned the tables on the whole thing because everybody had got so much vested interest. And I said, "Okay, I'm going home." And then there was a great kerfuffle. "You can't go home, you can't go home." I went home and didn't go to the meetings afterwards, and it took them quite a long time to come round to 5.1, which they did in the end, of course.
Yeah.
But that's the sort of stress, one feels like just throwing all the papers in the air and beating them on the head and walking away. It was so frustrating. But the other thing I'd like to mention about the 5.1 and its progress and so on, if you look back over the history of the record business, most of the innovations, I would say, many of the innovations anyway, have been made by the software companies, like Decca, like Philips, like EMI, and so on. And that evoked certain hardware changes and developments, and it all went on. But as time went on, in just about the time I left, when they shut my place down, all the development was coming out of the hardware companies. And the hardware companies, to my mind anyway, and many of my colleagues, didn't think the same way. Their goals are not the same. They're more interested in mass numbers and all this sort of thing. And so we've lost our way in that sense of controlling the way that developments go on. Yep. And finally, to make good 5.1 isn't easy. As somebody said over there, it's probably very pointed to the classical area, which is where I was involved. And we had to go out, and we were doing, as you know, experimental recordings, trying out microphone techniques and so on to find out how to do it. We had the old 1970s quadraphonic tapes, and we listened to those a lot and found what was wrong with those, and we actually were getting on very well. One of the things that sticks in my mind was we mixed a recording we had of Pavarotti, and it was a multi-track recording, so everything's available, and we put Pavarotti behind us, yes, and we put the orchestra in front, and that was quite a revelation to a lot of people, because it didn't matter how loud the orchestra was or how loud Pavarotti was, it was all very interesting. Whereas when they're all mixed up in front of you, everybody goes to the last dB of adjustment to get the balance right. And because they're in physically different places, you'd be amazed how this thing sounded. I've heard it, and about four or five of my colleagues have heard it. To my knowledge, nobody else has ever heard this. And it was quite dramatic. It's not, well, it could be real, I suppose, in the sense that you could have the artists in these situations, but it did open up a huge range of possibilities which have really perhaps not been explored.
Yes.
Following a demonstration of this to our chairman, he said to me, "Well, I don't know why you bother with all these technical things." And that was one of the last things he said to me. So that's unfortunately the way the recording industry has gone. And there was a paper at AES in Amsterdam, can't remember who gave it, but I found it really fascinating, where the guy was talking about the death of quality and the rise of MP whatever and iPods and this and that. And he said, well, the customer takes the least point of resistance in acquiring their music, and if it's on an iPod or it's in your telephone or whatever, it's so easy, quality is way down the list. And therefore, things have declined in quality, or perceived quality perhaps, but convenience has risen. But he said, the day will come when we're sort of saturated with the ease of acquiring it, and then perhaps the quality can grow again, because that'll be the only other variable they've got to adjust. So there's hope for the future.
Everyone hears live sound all the time. You know when it's right and when it's wrong, and somehow people have come to expect, radios sound like little plastic boxes and not like reality. But you made a lot of points, and it's going to be hard to get back to them all. But one of the problems the music industry had with 5.1 was the quality of the centre speaker. Often, a mid-priced home theatre system has got a rather nasty centre speaker. So the music industry wouldn't mix into that anyway. But they did lose their way because they didn't have an advocacy group. And even in these days when you do have an advocacy group, all meetings you're warned off about antitrust and things like that. It was much easier before antitrust lawyers came to the meetings as well to say, well, you can't discuss that, or you can't compare notes on this, that, the other. And you're right, it was engineering-led, it is engineering-led. We were told, beginning of Blu-ray and HD DVD, why is there a new format? Nothing to do with high quality. China is now building all the DVD players so cheap that we, the big Japanese companies, can no longer compete, so we need a new format. So that's the reason for the format. And then the studios say, great, we can sell the movies all over again. And it's all coming from the wrong direction.
Bob, I'm sorry, and I apologise to the audience as well. We've overstayed our 9 o'clock limit here, so we'll have to call an end to it, despite the fact I'm sure there's lots more interesting questions. Bob, once more, thank you very much.
Thank you, guys.